Hello, welcome to Electrical Circuits part number 12, Resistive Capacitive Circuit Analysis or RC Circuit Analysis. So now we're going to mix resistors and capacitors together. We have a 60 Hertz series circuit here. Remember, we trace it, there's only one path, so that makes it a series circuit. And we're given different values. Now we're going to be using the Pythagorean theorem from this part on. C squared is equal to A squared plus B squared. So we're based off the right triangle for a lot of our calculations now, besides Ohm's law and the power formula. And on the right triangle in electricity, we put it up in the top right quadrant of a Cartesian graph. And so the y-axis we put for the right triangle off to the right side so that we can see it over the y-axis of the Cartesian graph. With that being said, now the line that runs over the x-axis, that is always going to be the resistive part of our circuit. The vertical line on the right will always be our reactive part of the circuit, and then the hypotenuse, the longest leg, will always be our total. Now we can use this part of the Pythagorean theorem. We can use this with our current, with our voltage, with our resistances, or our ohms on here. Now, whatever we make the value for one side, the other two sides has to be of the same value for this to work. So we're going to start off and introduce you with a new letter, the letter Z as in Zulu, which is a symbol for impedance. In AC, impedance replaces total resistance because between the resistances, the capacitors, and then when we bring inductors into it, they impede the flow of current. So it's a little bit different. You can look at it the same way, but it's different terminology. And so using the Pythagorean theorem of C squared is equal to A squared plus B squared, we have to throw a little twist in with it. Z, our impedance, is going to be where our C squared was, but we're going to take it to, we're never looking for C squared, we're looking for the singular unit, not the squared unit. So we'll take Z is equal to the square root of R squared plus X sub C squared. Both of those are in ohms. Z, the impedance, is also measured in ohms, so all three legs are the same quantity. So we'll plug in our 12 ohms squared and our 16 ohms of our capacitive reactance squared, and that gives us 20 ohms impedance for this circuit. Again, that 20 ohms impedance, you can look at it kind of similar to what in DC would be total circuit resistance. So now we're going to be looking for our currents. So our current total is going to be equal to our voltage total divided by our impedance. Again, we would replace the R with the Z, and we would be using RMS values, the 70.7% of the AC values. And so I sub T is equal to 240 volts divided by our 20 ohms impedance, giving us 12 amps total. And I sub T, this series circuit, is equal to I sub R is equal to I sub C. So we can populate I sub R and I sub C with that 12 amps since current remains constant across all devices. And now we're going to be looking for our voltage drop. So the voltage drop at the resistance is I sub R times R. And so we have the current of 12 amps times the resistance of 12 ohms, giving us a 144 volt drop at the resistor. V sub C is going to be equal to I sub C times X sub C. So our 12 amps times 16 gives us 192 volts. Now, here's where our quick checks do not work because we can't add those two voltages to get our total voltage as we would in a purely resistive circuit, and that is due to the reactance. Now we're going to be looking for our power. We sometimes call this true power in an AC circuit. True power is measured on only the resistive part of the circuit. So to get our true power, would be the resistance, or the current rather, at the resistance, so I sub R, times the voltage of the resistance, so I sub R times V sub R, will give us our 12 times our 144, which gives us 1.728 kW. That is the only one I measured in wattage when we get into AC, is just on the resistive part of the circuit. Now, here's another new term, V as in Victor, A, and that is volts ampere, is what it stands for. It is also called our apparent power, the power that it appears that the circuit is producing. And so VA is equal to I sub T times V sub T. And so our 12 amps times our total voltage of 240 volts will give us 2.88 kVA. And so it is measured in volts ampere and not watts. That way we can distinguish the difference. Now we're going to look for our capacitance, so we'll use that same formula we've been using, 1 divided by, open your parentheses, 2 pi times your frequency times x sub c. So we have 1 divided by, open our parentheses, 2 times pi times our 60 hertz frequency times 16 ohms capacitive reactance, giving us 165.8 microfarads. We can find our bars sub C is going to be equal to, and we're using the pi formula here, it'll be equal to I sub C times V sub C. So our 12 amps times our 192 volts will give us 2.304 kVars. Now we can go into the power factor. Power factor is a rating that we use in here, and to get our power factor we take our true power and divide it by our apparent power. It's always going to be a number between 0 and 1. It's actually a percentage, 1 being 100%. So our power factor in this case would be equal to our, taking it back to decimal, 1,728 watts rather, divided by our apparent power of 2,880 volts ampere, which would give us a 0.6 or 60% on our power factor. Now we are going to use our power factor here also to get the angle theta, is what the Greek theta and the angle sign before it. The angle theta is actually our phase angle. And so we're going to take the arc cosine, or cosine to the -1, times our power and then add in our power factor. So angle theta, cosine -1, the 0.06, would give us 53.13 degrees. Now we could really round that to 53 degrees because we're not circumnavigating the globe. If we was navigating the globe, we'd know minutes, degrees, minutes, and seconds. Here we just really need the degrees, but I went ahead and put it in as a 53.13 degrees. The power factor is the reason it can be a percentage is because it is a ratio. A ratio is a percentage, right? So it's a ratio of the true power to the apparent power. Now we have all our different calculations for our expected value that we can use as a base for our live readings that we'd go out and make on the circuit. That concludes part 12 of the series. Thank you.